8.3, Introduction to Decision Trees. Why I jump to a different topic here, decision tree. Yeah, the reason is very simple. In order to understand the binary exponentiation method clearly, we need to organize data. So in algorithms, organizing data is very important, a very important step. Yeah. Here, we use the decision tree way to help do our implementation in a very clean way. Yeah. All right, so let's start this topic. Actually, this decision tree topic can be used in many different situations. So other than this place, in several other places, we need to use this method. Yeah. So that's why we use this chance to study this concept. So what is decision tree model? Now, it is very simple. Decision, related to decision. Yeah. We need to make many decisions. Yeah. Yeah. So for this decision tree, typically we use it in two-way decision. So many decisions have k-way decision, right? More than two. You know, when you make decision, there are several possible cases. Now, here we only look at two possible cases. So two-way decision. Yeah. So each decision has two possible outcomes. Yeah. So that's the one, the most commonly used decision type. So we just look at this type, the simplest type. Yeah. Its graphical structure we call a full binary tree, a special binary tree. Yeah. Yeah, we know binary tree, but here we call it full binary tree. So what is a full binary tree? So let me explain this special binary tree a little bit, the key property. Yeah. First, it's different from complete. So we learned a complete binary tree before. So it's different from complete binary tree. Yeah. Later we will compare. Okay, complete binary tree, full binary tree. Yeah. Each node has either two or none children, child nodes, children. Okay, cannot have exactly one child node. So that is the key property. Yeah. Here, let me draw this diagram. This is a full. So each node either two, right? Either two or none. None. No child. Okay? Yeah. Only these two cases. If I give you a non-full binary tree, you can look at this example, especially this place. You can see there is one node. It has only one child node. That's not a full. Yeah. So that's simple. Okay? Yeah. Now, if we compare it with complete binary, this is complete binary tree. You can see complete binary tree is also full. Yeah. So that's no problem. Also full. But all the levels are full. All the levels are full. Yeah. So you can see the general full binary tree, not necessarily complete binary tree, but not necessarily a complete binary tree. But a complete binary tree must be a full binary tree. Yeah. So, all right, next. Then in a full binary tree, we can see there are two different types of nodes. So we separate these two types. The first type we call internal nodes. Internal nodes. Yeah. Those nodes with child nodes. Yeah. Two child nodes. Yeah. Internal. Yeah. Then the second type leaf nodes. Leaf nodes without child nodes. Yeah. Non-zero without child nodes. Yeah. Sometimes people also call external nodes. Yeah. Leaf nodes, external. Yeah. Just two different names. Yeah. All right. Next, we want to look at some simple properties of decision trees. Yeah. First, each node has either 2 or none. Yeah, that's the key property. So we list it again, put it on top. Yeah, that's the first one. Second, the number of external nodes equals the number of internal nodes plus 1. Yeah, so you can check this case. The number of leaf nodes is always 1 more than the number of internal nodes. Yeah. How can you show that? Yeah. So this rule, how can you show that? Yeah. By mathematical induction. Okay. If you really want to show this formula, so you can do it by mathematical induction. So it's a simple practice exercise, induction. You can show, yeah, but I won't give you this question in your homework or test. Okay, all right, or quiz, yeah, no such question. All right, this equation or rule or property only true for full binary tree. Here you can see if it's not full, yeah, this case won't be true, right? It won't be true. Yeah. All right. Then the root node could be a leaf node. Yeah, it's possible. The root node, you only have 1 node, right? At the root. Yeah. In this special situation, the root node is also a leaf node. It's possible. Yeah. The total number of nodes of a full binary tree must be an odd number. Yeah, you can get this result easily. Suppose the number of internal nodes is A. Okay? Yeah. The total nodes, number of internal nodes plus the number of external nodes. External equals A plus 1. Yeah. Then you get 2A plus 1, and that is an odd number. Right? Yeah. So that easy. Yeah. Odd number. Yeah. If you see a binary tree has even number of nodes, one thing you can say, it is not full binary tree. Yeah. That's simple. All right. A decision tree corresponds to a full binary tree. So for this property, yeah, this property, so we have, from our textbook, yeah, standard textbook, but later we will see for some special cases, so this condition can be released, can be relaxed. Okay, so when we think about extension for this case, yeah, because later if we look at a search algorithm, we cannot get a full binary tree for the decision tree. Yeah, so later I will find a chance to show you that example for search algorithm. Okay, yeah, full binary tree. Because sometimes when we make a decision, we may only have one outcome, not 2 outcomes, 1 outcome. Now, search, when you do the search, when you get to the last element, or when you get to some point, yeah, so search, binary search, right? Binary search, yeah. At some point, you can only go to one side, not 2 sides. 2 sides, then binary, 2 outcomes. But if you get to a certain point, you can only go to one side. There, 1 outcome, not 2 outcomes. Yeah. So that kind of thing will make us to modify our decision tree requirement. Yeah, so we will see that later. Yeah. All right. Next step, use examples to show how to use the decision trees. All right, so let us finish this video first.